Alright, in this video we'll be going over vectors, more particularly the component and projection relationship between two vectors. So to really start and understand where we get these relationships, we must first look at the equation that's very crucial to understanding it, which is the A dot B relationship. So with the dot product, that is essentially a multiplication between two vectors. It's how you multiply two vectors together and get an overall magnitude. So a dot product is a relationship that leads to a scalar product. So you can't dot a vector with a magnitude, or scalar, I should say, and you can't dot two vectors. This only works when you have I, j, and k components. We're only dealing with I and j for now, k eventually later. So what this overall equation is in general terms is the magnitude of A times the magnitude of B times the cosine of theta, where theta is the angle in between the two vectors A and B. So we won't go in a lot into where this equation really comes from. We're just going to look at the relationship between the two vectors, the angle, and how we can use that with we know that is equal to A dot B to draw a lot of different conclusions. But once you understand this relationship, a lot of classes become way easier. Let's say memorizing how to use this now helps you for this class at this point in time, but understanding how to use it today or tomorrow will help you throughout a lot of college. So it's really important to help understand this, or take the time to understand this, and with each point you can. I'll say it took me about more than a year or a year-ish to really understand how to use it, and that's when I came to teach Calc 1 again. But it may click now, it may click 2 months from now, it may click a year from now. Eventually, it will click. But it is just know that it will take time, take effort. But if you really flex your muscles and trying to understand the concepts, then it'll become easier to use it and easier to understand. So from that equation above we just had, what is the component of A onto B? So what we're really asking when we say what is the component of A onto B, we're saying how much of vector A, and we have a diagram down here below, how much of vector A is in the direction of vector B. So we're trying to get this overall length here in between where the two vectors are, their tails start, and their relationship with each other, to where we have a right angle there to the other vector. So we're trying to figure out what that length is. And so we're going to use that other equation in a second that we just had above. But in order to really get that relationship, we must make a triangle. So in this triangle, our hypotenuse is going to be the magnitude of A. It really has the direction of A, but we're just going to give it the magnitude of A, but have that angle theta still. And where our side length at the bottom is going to be the component of A onto B. Now, we're going to get a relationship between these two. So between A, our component, and our angle. So going back to trigonometry, geometry, however long ago it may have been, for me, that was a really long time ago, but for you all, hopefully not too much. I remember the mnemonic device SOHCAHTOA, and we're going to start at ka, where we have cosine theta equals the adjacent component. In this case, our adjacent component is going to be the component of A onto B. All over our hypotenuse, where our hypotenuse is the magnitude of vector A. Now we want to solve for this component, so we're going to multiply our A over. So we have the component of A onto B equals the magnitude of A times cosine theta. Now, we can calculate cosine theta. You can usually calculate magnitude of A pretty easily when we're given two vectors. But to calculate cosine theta is not typically that easy. So instead of just trying to go straight and solve this equation, we're going to go and manipulate our equation we have right here to get A cosine theta in terms of something that's more easily calculable. So A cosine theta, magnitude of A cosine theta, I should say, equals A dotted B over the magnitude of B. So all we did was we just divided the magnitude of B term in our product on the right side to both sides to where we have, which is essentially the component of A onto B. So by this relationship, we can then say our component of A onto B is going to be A divided with B over the magnitude B. So again, you can memorize this or you can truly understand it, and then it would help you for the long term. Because understanding this will be even more helpful to understanding the projection. So remember, this value here, we just found here, this is a scalar quantity. Scalar. That represents this length of how much A is in the direction of B. That portion of that vector A is in the direction of B. So that's a very important thing because we're eventually going to use this for a vector projection. So this is how far A is in the direction of B. So that's what gives you this little length here, broken up by those two blue lines there, and then it's underneath the very bright blue component of A on the B. So now we're going to use what we figured out there to figure out the projection. So what would the equation for a vector projection of A onto B be? So the projection of A on the B is going to be the same thing, except it's going to be a vector. Our resultant quantity should be a vector. So that's what the big difference here is. So we're still going to have that same magnitude that we have as the component, but instead we're going to have a vector that's in the same direction as B. So we're thinking about this logically here. So we know we're going to have the same magnitude as our component from before. So we know it's going to have that portion, the component of A on the B. We know we're going to have this length. And remember, this is a magnitude or scalar, however which way you want to denote it. But it's going to be the same direction as B. So if we wanted to denote a direction in terms of a vector, we normally write that as a vector hat. Hat essentially is a unit vector. You'll see this more in physics 299, which is physics 2, where you go over vector fields and differentials of voltages. But for now, just know that it just means the direction of something. It has a magnet, and this vector has a magnitude of 1. So it's still a vector in terms of it has a magnitude and a direction. But typically, it gives a vector direction, the unit vector. It gives you the proportion. If it were to go 1 unit length, what direction does it go in the x direction, the y direction, and eventually, when you get to calc 2, the z direction. So to get our unit vector, we however have to write it as here. I'll write B at right here. It's going to be your vector B divided by the magnitude of B, and this should make sense because if you just calculated vector B or just calculate the magnitude of vector B, it should be the magnitude of B. But if you divide it by the magnitude of B from each component of your vector, that means your overall resultant vector magnitude should be 1 because you're essentially just dividing the magnitude by itself. But remember, this doesn't go to 1 if we leave this as a vector, right? Because as long as this is a vector, it doesn't go to 1 because you can multiply and divide vector quantities by scalar quantities, but without changing the degree of that information. Degree means that magnitude is 1 degree. Having a scalar and direction is 2 degrees. And there's more that you eventually get into. They're typically called tensors. But that's much further. That's more like in fluids, about 2 years from now. But with this degree, since magnitude doesn't change the degree of vectors, we know that when we divide by whatever magnitude, it'll just change the magnitude of that vector. It doesn't change the direction at all. We'll still have those same components proportion. So when we go to write this as an equation, our component of A onto B is going to be that one we had before, which is A divided with B over magnitude of B times B hat. Remember, we already said B hat is going to be your vector B divided by the magnitude of B. And you can simplify this as A divided with B over the magnitude of B squared, all times by vector B. So remember, this portion here is a scalar quantity. This portion here is the vector. So this is the part that gives it direction. And you can think this is the overall magnitude of your vector. And this is the overall direction of your vector. But when I say vector in this case here, instead of saying magnitude and direction, I'm just denoting which portion of what is that. But this magnitude here is 1. This is the magnitude of your overall vector, if that makes sense. All right, so that is our projection of A on the B. Now we're going to actually start calculating some stuff here. So if we're given these two vectors, A and B, where A is 2y minus 4j and B is I plus 3j, we're going to calculate each portion of it by itself and then plug it into our overall equation. And this is typically how it would look like on a test. They'll prompt you to solve for each part, and then you plug it in. So the magnitude of A is going to be the square root of the components squared added together. So we have 2 squared plus negative 4 squared, which will equal the square root of 4 plus 16, which equals the square root of 20. Remember always to simplify. So you can break this up into the square root of 4 times square root of 5. And then you can factor out that square root of 4 to be a 2 times root 5. Now vector B is going to be it's going to be square root of 1 squared plus 3 squared, which is equal to the square root of 1 plus 9, which is equals to the square root of 10. So I'm going to start boxing these. It's a good habit to get into boxing your answers. So A divided with B, so this is going to be, simplify this out, or we're going to plug everything into it. 2I minus 4j dotted with I plus 3j. So the way a dot product really works is that you multiply the components that are going into the same direction with each other. So I's are going in the same direction as other I's. J's are going in the same direction as other J's. K's are going in the same direction as other K's. But remember, we're still dealing with these I's and J's now, but I want to make sure you all understand that. So then this would be 2 times 1 plus negative 4 times 3. Overall, you'll get 2 minus 12, which equals negative 10. Now there's an important distinction I want to write out here. So if you dot an I with an I, remember that equal 1. But if you dot an I with a j, that should equal 0. So this goes to show that if you dot two vectors together that are perpendicular to one another, their overall resultant will be 0. So that's important to know because sometimes you'll be asked to find a vector perpendicular to this, to whatever portion. But this is a important thing to remember. So now to find the component, just remember our equation. A dotted with B over the magnitude of B, which we're going to equal the dot product, which you calculated, which is negative 10, over magnitude B, which is square root of 10. And we can simplify that out. So you multiply by, you can rationalize the denominator, or realize that you can just cancel out square root of 10, which will equal negative square root of 10. All right. Now the component should be, so the projection should be A divided with B over the magnitude of B squared times the vector B, which will equal the dot product, which is negative 10, over the magnitude of B squared, which is the square root of 10 squared, all times by vector B, which is I plus 3j. These will cancel out. So you're left with a negative I minus 3j. Our last portion is to solve for cosine theta. So for cosine theta, remember our equation right up here. A dotted with B equals the magnitude of A times the magnitude of B times cosine theta. So all you have to do is divide the magnitude of A and B to the other side. So A dotted with B over the magnitude of A times the magnitude of B. And really make sure you keep your vectors, your vector lines over all of your things. I've been pretty consistent about it, but I want to make sure that you all know that you will lose points if you don't always put your vector over your thing. So here, I lost points right here. That was part of the problem, but either way, you still want to make sure you put your vector line over your vector. All right, now we have the dot product, which is negative 10 over the magnitude of A, which is 2 root 5, times the magnitude of B, which is square root of 10. So we can go ahead and multiply everything throughout. So we have negative 10 over square root of 50. Didn't come out right. We can simplify our square root and our 10 over 2. So we have negative 5 over the square root of 25 times 2. Square root of 25 comes out, and we're left with negative 1/2. All right, so quick review. This is how much A goes in the direction of B. This is the vector of A going into B, going in the direction of B. And this is the cosine of the angle. So this shows that per 2 for every 2 that B moves, A would move 1 in the opposite direction. You don't really need to understand that, but that's what this angle is pretty much saying. All right. Just as a quick note to everybody, this is very likely going to be similar to a problem that you'll have on your test. So will this one. This is also a very important problem to know how to do. Is your My Math Labs #1 on your homework for Unit 3. You should definitely do this one. This is very helpful. I put a star by it because I can almost bet money you'll have a problem like that on your test. And just go through. This is on the worksheet I posted. But I mean, again, go to your My Math Labs. Go through the how to solve it or wherever you need to understand this problem. It's very important. But if you understand everything I did in this video, then you should be able to understand how to do this problem very well. If you do have any questions, please comment below. Send me texts, send me emails. I'm pretty quick to respond. However, I won't solve things for you, but I will be glad to give you some clarifications But yeah, good luck on your test. I hope this helps. Good luck.